totally different.
That's interesting.
Is that a generic one? Or?
Okay, so we should get started. Our colloquium speaker today is Andrew MacFadyen from New York University. He got his PhD at Santa Cruz, where he survived being the student of Stan Woosley.
Easily.
His paper on collapsars has 1,300 citations when I last looked. It's one of the seminal works on collapsars and sort of show that long gamma ray bursts can be explained by that model. After Santa Cruz, he did 2 postdocs at the Institute for Advanced Study and Caltech. He did a sabbatical here for a half year, so you're probably familiar with him. So we'll just leave it to Andrew to give his talk.
You also worked here.
Yeah. Yes.
Okay.
I worked on the education project with Phil Souther and Erwin.
Take it away.
Okay, great. It's always great to be here. I always enjoy visiting, and I'm enjoying it being here right now. What I'm going to talk to you about today is something I consider really exciting, and it's work, which is this is a picture that really tells a lot of the story, which I'll go into more detail in this talk. But the basic idea is we're looking at disk accretion, where instead of a point mass at the center, we have a binary. And I'll explain the context in which these are interesting. But there's a couple of interesting things to note right away. First of all is that there's kind of a cavity that forms, and that's due to torques driven into the disk by the binary. But the cavity isn't empty. In fact, gas makes it very nicely onto each individual black hole. Let's call these black holes for now, and forms mini disks around each of them. In addition, gas that's trying to make it into the binary is flung out on streams. Like maybe half of the mass goes in, the other half is flung out and impacts the wall of the cavity and causes it to be eccentric. So the binary is actually closer to one side of this cavity. And in addition, these streams pile up into a lump. And this lump has its own frequency that orbits around. And it periodically gets too much mass into it, which is dumps onto the binary. So these are things I'm going to discuss in detail. This is work done at NYU in collaboration with Zoltan Hyman at Columbia, and the postdoc Brian Farris has done a lot of this. And my student Paul Duffel, who's now at Berkeley, wrote this code. And it's a very nice code, and I'll describe some of the technical details that make this project and others possible. Okay, so the basic story, just to set the physical picture, is for binary supermassive black hole accretion, is that all bulge galaxies have supermassive black holes at their centers, and this mass range of 10 to the 5 to 10 to the 9 solar masses. And during hierarchical structure formation, when galaxies merge, the massive black hole binaries can form in the merger remnant. And then, as the binary the black holes interact with the stars, they can be driven to the center, and then eventually they get close enough to emit gravitational radiation. So I'm going to discuss this process, but what I'm really going to focus on here is a circumbinary disk. So gas is also driven to the center and starts to orbit the binary black hole that's at the center. Okay, so why is this interesting? Well, for many reasons. Very importantly, supermassive black hole binaries may be detectable by an ELISA-like instrument during in-spiral. But even kind of quite exciting, pulsar timing arrays are also capable of observing more massive black holes in the 10 to the 8 to 10 to the 9 solar mass range at redshift 1 or so. So the really exciting thing about there being gas is that this may be a detectable electromagnetic counterpart to the gravitational wave source. So that's very important for both for finding the source, but also learning about the physics of it afterwards. So it helps with source localization. And in addition, it may even help with cosmology, because these binaries can be standard sirens, where you get the distance from the gravitational waves and the redshift from the electromagnetic signature. And so we can also learn about the rates of these mergers, so we know how many of them are happening. Okay, so the merger rate just depends on the fraction of close pairs. And then if we know the density of these things per cubic megaparsec and the time scale for merging, we can look in surveys like this and estimate a merger rate of this order. So, and this is consistent with semi-analytic galaxy models. So we're going to look for them with ELISA, and that detects things at 0.01 hertz, and it detects this range, 10 to the 5 to 10 times 10 to the 7. And their prediction is that there should be a few to a few hundred per year. So this is uncertain, but it's predicted that there should be a good number. Pulsar timing arrays detect these more massive ones with periods in this range. And these may be detected as well. And also the square kilometer array is detecting more pulsars, so that'll improve these pulsar timing arrays. It's very important. Okay, so the general picture is that viscous stresses in the disk drive angular momentum out through the disk and allow gas to migrate inward. But so that would be true for a single point mass at the center. But when there's a binary at the center, there's an additional source of torque. So tidal torque is due to the binary. And that adds angular momentum and can actually drive gas outward. So you have this competition between viscous stresses allowing gas to accrete and torques from the binary pushing it outwards. So what's found is that they balance. These two torques are opposite, and they balance at about a distance of twice the binary separation. So you might think that the binary would carve out a low-density cavity at its center. And there was some worry that the binary may merge without any gas around it. So it would be a dry merger, and it wouldn't be visible electromagnetically. And that's what I'm going to argue here is really not correct at all. We find that there's plenty of gas around it, as I showed in the first picture. So the other thing that we can look at is at first the binary is not close enough to emit gravitational waves. But as they get closer and closer, the binary starts to decouple from the disk because gravitational wave emission drives the black holes to merge. So it'll decouple from the disk. And we want to see what that will look like electromagnetically as the black holes peel away and merge. Okay, so the basic questions we want to answer by simulations is how hollow is the cavity? So is the accretion rate really suppressed by the presence of the binary? And we already know the answer to this is no. So does the binary leave an imprint in the accretion rate? And that's going to be very interesting. And it makes some predictions for what we can look for observationally. And as you can well imagine, it does affect the accretion rate quite drastically. And also, the question, just kind of theoretically, is how is the accreting mass distributed between the primary and the secondary? So depending on the mass ratio of the binary, the secondary generally accretes more. So, and I'll show that the binaries are driven towards equal mass. Okay, and then how are the spectra that we detect from galaxies at the centers of galaxies? How are they modified by the presence of the binary? And I'll show some multi-band predictions for what we expect. Okay, so there's been a lot of work done in this field. Very early work by Goldreich and Tremaine, kind of angularly averaged 1D stuff. And a lot of it was, I think, motivated by looking at planetary rings where gaps are seen. But there's been quite a lot of work done on this over the years. And a lot of them use kind of approximate angularly averaged tidal torque formulae. So those turn out to be, I think, sometimes misleading. In 2D, as you can well imagine, gas can kind of get in even if there are torques that are trying to keep it away. And that's because gas isn't just cold particles. There are pressure gradients, however small, which can allow gas to kind of sneak in onto the binary. But there's still these 1D treatments are still useful for kind of qualitative features of accretion. But as I'm going to really emphasize in this talk, they fail to capture these really important non-axisymmetric features, such as these accretion streams that we saw in the first slide. Okay, so I started working on this in 2008 with Milos, and we found some really interesting things for an equal mass binary. But as I'll show, we excised the binary. So we just had a disk with an inner boundary condition, and it was orbiting in the potential of a binary, but the binary wasn't on the mesh. So we couldn't really follow the gas as it accreted onto each individual black hole. But because it's 2D, we could do many, many orbits, and we could follow it at very high resolution for viscous time. So we can allow the disk to really relax viscously and accrete for a viscous time, so we could really get kind of steady state solutions. And that's what I'm going to focus on in this talk. There's also 3D simulations that have been done in the Newtonian and the relativistic limit, those tend to be computationally expensive, and a lot of them still excise the central part, which is really where a lot of the interesting stuff goes on. And so it's hard, and it's also hard to run them as long. So I'm going to focus in this talk on the two-dimensional simulations, although there are caveats that 3D may be important for some of the things I'm going to mention. Okay. So the 1D models, as we mentioned, kind of suggested that accretion would be choked. And that's, in 1D, if you sum over Lindblad resonances, you can calculate this parameter G tilde, which is like the ratio of the tidal torques to the viscous torques. And they show a transition, this is m dot of 1, and this parameter here corresponds to 4 times 10 to the minus 3 for mass ratio. That's the ratio of the secondary mass to the primary mass. And what it seems to show is that for lots of mass ratios of interest, the accretion rate goes to 0. So there's this transition where the tidal torques are just keeping the accretion at bay. It's not allowing any gas to get in. Okay, so that's the prediction from 1D. So the basic point of this talk actually is to look at what happens when we drop the assumption of axisymmetry and just look at two-dimensional effects. Okay, so numerical method, I'm just going to quickly mention what's novel about the code in this talk because it turns out to be quite important. And as some people here, or actually quite a few people are familiar, we solve the equations of hydrodynamics. And here they are. You don't need to know them in detail. The main point is that it's flux conservation. So we're looking at a set of conserved variables like mass, angular momentum, and energy. And they're changed because of the divergence of fluxes. And so, for example, everyone's familiar with mass conservation, right? It just says that the change in the density is changed because of the divergence of a mass flux, which is just the density times the velocity. And you can integrate this using Gauss's theorem, and you find that the total mass in a zone, if you just integrate over some finite volume, is given by the surface integral through the faces bounding that volume. And that's, in fact, the technique that we use, and it's called the finite volume scheme. And we write the same thing. In addition, these are called advective fluxes of energy, momentum, and mass. And there's also fluxes of momentum due to pressure gradients, which are very important. So that's what makes us hydrodynamics. Again, these are called Euler's equations, but we have viscosity as well that makes it Navier-Stokes. And the method is that in 1D is that you have a set, you have these vectors u that are defined on some grid, and you march things forward in time by calculating the fluxes through these spaces. So there's time, and so this is a space-time diagram. And the standard technique is to use a mesh like this that's fixed in space, and that's called an Eulerian treatment of hydrodynamics. And so basically what's happening is in integral form, we update these conserved quantities by their old values plus some difference in fluxes through their faces. Here's one face bounding the zone. Here's the other face. And if we know the fluxes over this time step delta t through these faces, we can calculate the new mass, energy, and momentum in the zone. Okay, so that's just some technical stuff. The only point I wanted to make is that those faces don't have to be fixed in space. They can actually move. So this is space-time. So it's moving at a fixed velocity to the right and to the left. If those faces move, we can kind of subtract out the advective flux due to boring motion. Just like the Keplerian motion of a disk, if the faces move with that gas, then there's no numerical fluxes and everything's really, really accurate. So that's the only point I wanted to make here. So that's what we do. We solve on a frame where the faces move. And that allows us to have a lot of accuracy. So the first choice of motion, this is just a cartoon of what we use. We use a mesh like this, cylindrical coordinates, and we're looking face down on it. And you might imagine if you have rotation, like for a binary or for a disk, you'd want the mesh to rotate. And so that's OK, and that's actually good in the central regions. We'd want some mesh like that. So if the fluid is moving with angular velocity omega, if we move these faces with velocity omega, then there's very little numerical flux. And the only fluxes we calculate are the interesting fluxes due to pressure gradients. OK, but you can also imagine, this is the whole thing. This is the whole technical improvement that turns out to work really well, is we use a mesh like this. It's a very simple thing, and surprisingly hasn't been done before to my knowledge. This is called Disco, because it's a disk code, Disco. But the only thing, so this is all you need to know. Look at this zone. So it has a face to the left and to the right. But now, because the mesh sheared, it now just has two neighbors inside. That's all. And so we can calculate a flux as if this were a face and this were a face, right? But that has a huge technical advantage. It allows us to have, of course, there's really high resolution, but the whole disk shears, and that means that we maintain a really high degree of accuracy. And this was inspired, actually, when I was here on sabbatical last time. I went to the De Cordova Sculpture Park, which is a really cool place. I highly recommend it. And I said, there's this guy, Lars Erik Fisk, he turns things into spheres. That's he's a sculptor. And I loved this one. This is actually the museum, which is a brick building, and he turned it into a sphere. And it's really cool because you can see this thing. The bricks have two faces. And also, you can think of the sphere as a stack of disks, and those disks can differentially shear. So this is basically what we do, more or less. So here's a more technical picture of it. So you see the inner ones in a Keplerian disk are going faster, and as you go further out in the disk, they're going slower. So the mesh is shearing, and so here's how we take a zone. We take two faces outer and two faces inner, and everything else is the same. So it's really kind of nice. And we solved, this is actually code that does relativistic magnetohydrodynamics, but most of what I'm going to show you today is Newtonian hydrodynamics, because we're on scales larger than the event horizon of the individual black holes. So we want to see the global picture on large scales. And so this moving with the fluid is called Lagrangian treatment. And this is not exactly Lagrangian, and I think that's the whole key. We don't overdo it by trying to move exactly locally with the fluid everywhere. We know what the flow symmetry should be, and we exploit that to write a code that does that. And so it really, really incredibly cuts down on advection errors and allows us also to take much longer time steps because the gas is supersonic. And it's moving at Mach 20, and so if the mesh moves with it, we're limited by the Courant condition due to the sound speed locally co-moving with the fluid. Okay, so here is Disco performing the first simulation that I did in 2008. This is a redo of the earlier simulation. But look what happens. There's the binary rotating. In this simulation, the center is cut out. But look, even though it's an equal mass binary, the cavity becomes eccentric, okay? So first of all, there's accretion streams that are being ripped off of the inner part of the disk, and they're falling through the inner boundary. And then the cavity is becoming elongated, and you're starting to see these pileups of these spiral waves that are forming lumps. And you'll see that better in the future. But so this is already very interesting. What we find, even though it looks like waves are going out, mass is actually going in, and it's accreting through these streams into the inner boundary and accreting. And so that's what we calculated, and we found that, in fact, there was plenty of accretion through this inner boundary. But of course, we were worried that there's gas flow inside it, actually very important gas flow, and that might back react on the fluid, and the solution is suspect for that reason. So what I'm going to show you now is that we have the whole domain. So we simulate all the way to the center. So we have all of this, and the black holes are put on the grid as softened gravitational potential. So they move with the grid, and they're allowed to accrete. Okay? So we're going to see if these things still happen. Okay, and by the way, you can see how long this runs. It keeps on going, and that's really good. So we can make sure we relax to a steady state solution. Okay, so the improvements that we've made are to include this inner cavity, because it turns out, really important. That's where a lot of the interesting gas dynamics happen. And so we want to attract the accretion onto each individual black hole and account for important gas dynamics near the black holes. So in particular, they form these mini disks, and these disks share mass back and forth. And also, as the accretion streams slam onto the disk and join the disk, there's shocks. So the gas is shock heated and gets hot and emits brightly. So this is the opposite of what was thought. Instead of there being a cavity with no radiation coming from it, when we follow the dynamics onto the black holes, we find that actually there's a huge amount of energy released. So these are going to be bright sources, not dim sources. And these are really, all I'm just going to say, these are really good methods. They work really well. I can bore you with the details later if you care. And then, so we evolve much longer than a viscous time to reach quasi-steady state. And then, of course, what we do is we vary the mass ratio. So we want to know, and actually we can get to the Emery, or extreme mass ratio limit, which is a lot like a planetary system. And then we can go all the way up to equal mass. So all of those are of interest. And there's qualitative differences in the phenomenology. Okay, So what we do at first is we set up a grid in an intelligent way. And at first, and later I'm going to relax this, but at first we did isothermal. This is 2013. We did isothermal disks, and we held a fixed h over r. So that's the ratio of the scale height of the disk to the radius, so of 0.1. And we implemented an alpha law of viscosity, and with an alpha of 0.1. And we included the cavity in the computational domain. And in order to treat accretion onto each black hole, we have a sink. So there's a sink term that removes gas from each mini-disk on the viscous timescale of the disk. And so then we're able to run simulations for a really long time until we get into some sort of steady state. And so, for example, we can run much longer than a viscous time, which is many hundreds of orbits of the black hole. So the black hole is spinning hundreds and hundreds, sometimes thousands and thousands of times as gas gradually accretes onto them. And the ratio of mass ratios that we did is this, from 0.026 to up to 1. And all this shows is that there's higher resolution where the black holes are, as we would want there to be. So everything's really nicely resolved. Okay, and this is just to give you a visual sense of what happens. Here we go. So on the top panel, we're in the lab frame. So the binary is rotating. And here we're co-rotating with the binary. And the right-hand panels are just a zoom in. And this is a mass ratio of almost 1. It's about 0.6. And what we're showing at the bottom is the accretion rate onto each component. And you can see that they're both accreting. But it's not straightforward. It's not just at the binary frequency at all. It's a little bit hard to see, but this is the lump that I was talking about that's dumping more mass onto the binary at a much longer period. Okay? So there's low frequency modulation of the accretion, which is due to the gas being flung out by the binary into the disk and then being redumped onto it on a longer time scale. So if you see, I'll talk about later, if you see an observed frequency, it's not necessarily the binary frequency. In fact, for this one, it's dominated by this lump frequency. You can also see the black holes kind of share mass back and forth, and there's some sort of very complicated gas dynamics. But all this gas is being shocked, and it's glowing like crazy. So this is isothermal simulation, so we don't calculate the radiation yet, but I'll get to that soon. We'll actually calculate how this radiates. And also you can see that the secondary, which is the blue, accretes more than the primary. The more massive one accretes less than the less massive one. And in fact, because the less massive one is closer to the cavity. It's farther from the center of the mass, so it's near the gas, so it gets more of the mass. And that has important effects, which we'll see. So the accretion rate that we find, so way back in 2008, and now I think a huge number of people are starting to agree that the accretion is not at all significantly reduced by the presence of the binary. What we find is that gas, as you saw, just makes it in and forms these mini disks, and accretes just fine. In fact, it's a little embarrassing. We actually get higher. This is m dot that we get versus m dot for a single mass black hole, and so it's actually higher. If it had a time to relax, it would relax down to 1 eventually, but it takes a really long time. So it's actually sucking in more mass. So they're accreting at least as much as you would for a single black hole of the same mass. So the cavity is not impeding accretion. It's point number 1. The second point is, as we mentioned again, is that the cavity is eccentric. So we can measure this eccentricity, and you can see again here these little streams that are being ripped from the edge as the gas comes around. And again, here's this lump, and here's some accretion streams. And so this is seen now in many simulations as well. So many groups are seeing this. And what happens is that the accretion, if there's a little instability, that if this accretion string is flung out, that pushes the cavity wall away, and that kind of self-reinforces itself, because now it picks up less mass here, and then the one that's receiving more mass flings more out there, and that becomes unstable, and it forms this eccentricity. So then this imbalance grows. Okay, and so what we find is if we start with an initial condition, this is from Milosevic and Finney, we started with this initial condition. That was the kind of this one-dimensional idea that there'd be a cavity in the middle. We find as soon as we start it, the cavity fills. And as a function of mass ratio, I'm sorry, this is hard to see, the cavity changes size. So for low mass ratio, it's small, but for higher mass ratio, it gets bigger. And similarly, I apologize for this. Similarly, the eccentricity grows. So this is the eccentricity measured as a function of radius, and we see that there's a lot of eccentricity in the middle. And of course, it goes down to 0 in the outer disk. The outer disk thinks it's still just a Keplerian with a point mass at the center, but as you go further in, there's eccentricity grows. Okay, and then these kind of show the same thing. Okay, so we can compare with analytic estimates for the mini-disk sizes, and these are based on these Lindblad torques that were computed analytically by Artemovitz and Lubo in 1994. And their predictions are these cyan circles, and the color is the density time averaged in our simulations. So it looks like it matches pretty well. For many different mass ratios, we tried this, and we found in all cases that those predictions were spot on. Okay, and then the other interesting thing is the mini-disk has a time scale. So it's something like r squared over nu. And we find for the parameters that we're using in this first 2013 study that it's many times the binary frequency. So the mini-disks are persistent. They last. They stick around, and they modulate accretion. If accretion is variable in the outer part of the disk as it's being dumped onto the binary, it's kind of damped by the mini-disk, so it receives this fluctuating mass, but then transports it in more smoothly. So the caveat in this part of the talk is that we're using h over r of 0.1 everywhere, including in the mini-disks. So that if they're hotter, they could accrete right away and maybe wouldn't stick around. Okay, and we assumed alpha is 0.1 everywhere. So these are caveats to keep in mind. Okay, but nonetheless, we can do this for a bunch of mass ratios, and this is showing the difference between Q of 0.11, 0.43, and 1. And what you can see is pretty interesting. The secondary is always accreting much more rapidly and periodically for low mass ratios. And the primary has a very low rate, because it's just sitting there at the center. The secondary is kind of gobbling up all the mass because it's whipping around near the edge of the inner cavity. But as we increase the mass ratio, so 0.4, what we find is that the secondary is still accreting more, but it's closer. They're kind of both accreting, but it's no longer at the binary frequency. It's modulated at this longer frequency. Okay? And then as we go to equal mass, they accrete the same. But here, it kind of has this weird sawtooth pattern. The binary frequency is that short frequency, this high frequency, and then there's this lower frequency modulation with this type of shape. Okay, so that could be very important because recently there have been observations of periodicity observed in the optical. And so the question is that the binary frequency? So this is a bunch of different mass ratios from 0.05 all the way up to 1. And the green shows the secondary accretion, and the blue shows the primary accretion again. But now the red is showing a periodogram. So it's showing kind of the Fourier transform of the accretion rate. And what you can see at this mass ratio, 0.1, it's most of the accretion is at the binary frequency. You can see it there, right? There's some overtones, but it's mostly at that frequency. But as you go to higher mass ratios, then you're starting to be modulated by this kind of lump that's dumping mass on a different frequency. And the frequency shifts to a much lower frequency. So let's just look at 0.67. This is the binary frequency. There's a little bit of power there, but most of the power is actually at 1/5 the binary frequency. Okay? That has really important implications. That means if you're seeing a frequency, the actual binary frequency might be 5 times higher. That means it might be much closer to merging and thus have a much shorter lifetime and maybe not stick around as much. There may be more of these things than you'd predict if you assumed that the frequency you're observing is the binary frequency. So at the mass ratios we expect, this is the case, that this lower frequency dominates. Okay. And so there's a recent paper in Nature by Graham et al., which indeed detects roughly 4-year periodic signature. And the only point I want to make is that this periodicity does not necessarily correspond to the binary frequency. The binary may actually have a higher frequency. Okay. Another point is that the mini disks damp accretion variability. So if you look out in the disk and you calculate the accretion rate, it's highly variable, and the green is its mean accretion rate, but it's highly variable. Some of that variability is damped. So you mostly see this because the mini disks are receiving the mass and kind of smoothing out and damping the high frequency accretion. So that can be important. That also might depend on mass ratio. Okay, and then, so the other point is that how the mass ratio evolves into time depends on the time derivative. It depends on basically the fractional rate of increase of mass of the secondary versus the primary. So what we find in all cases is m2 dot over m is greater than m1 dot over m1. So that implies in all cases that this is positive and the mass ratio is being increased. That means it's being driven towards 1. So 1 is the maximum you can have. So binaries, by this accretion process, should be driven towards equal mass, which may be important. So if you have a long period of accretion, you might expect the mass ratio of the binary to be closer to 1. Okay, so before I told you we used an isothermal approximation for the thermodynamics of the gas. And so recently, we've improved upon that. And so now, instead of using this kind of isothermal prescription for H over R, we actually self-consistently balance viscous heating with radiation from the disk. So we assume an optically thick disk, and it's emitting from its surface like sigma t to the fourth, and we have an electron scattering opacity. And in these simulations, we've not included radiation pressure, but we intend to do that for the inner disks where it may be important. But we solve the energy equation, so we're solving self-consistently for the viscous dissipation in the disk and the radiation from the disk. So we can actually have some more realistic thermodynamics. And so I can show you a test just in 1D that shows it works. This is our initial condition, and this is Shakura-Sanyaev, which you'd expect it to relax to if this works. And you can see that after a viscous time, it does relax. So here's the pressure, and here's the density. It takes a little while, but starting from this initial condition, the thermodynamics work. So we actually get this. And the velocity is the deviation of the velocity, so it's actually quite accurate. So that works in 1D. And this is actually our 2D code written in 1D. So now we can put a binary into this scheme, and this is the picture that you saw at the beginning. So now, not only do we have this is the density again, showing this lump and the accretion streams, but now we can also calculate the dissipation in the gas and make a map of the photons coming out of it. So I'll let you see this. This is a movie of that first picture. And what's going on, again, is you see this lump? This is that longer frequency. Now it's going to be dumped onto the binary, and the accretion rate will go up. Then some of that mass is flung back out. In each stream, about half of it goes in and half of it is flung out, kind of like a tidal disruption stream. But now, because the disk is in the way, that gas piles up in the disk. Okay? And then it forms this kind of bright lump, which again will start to fill up and then dump another lump onto the binary, and the accretion rate goes up. And you see lots of interesting stuff. And this gas is shock heated and so on. So this is the origin of this longer frequency. So sorry, the lower frequency modulation of the accretion rate. Okay, so here we see a picture of the density. It's not a great picture, but the basic idea is that here is the lump and here are the accretion streams. But now, because we're calculating the temperature in the disk, we can calculate its emission. And this is what we see. So not only is the cavity bright, it's really bright. So right around each mini disk, there's plenty of gas shocking as it hits each disk. The streams are heated because they're shocked by gas hitting it from the side. And then the gas also that's flung into the cavity wall shocks and heats. So instead of being cold and empty and dim, it's actually a really bright environment. Not only that, it's actually brighter than a disk with a single mass black hole of the same mass, where you'd expect to be, you'd expect to get much more radiation, but you don't actually get more radiation out of this because there's energy in the binary that's flinging the gas. So it's not just the gravitational energy of the gas falling into the center, it's also the whipping around of the gas by the binary, which is releasing energy into the disk and driving these shocks, which light up like crazy. So what we think is that these sources are actually bright X-ray sources pre-merger. Previously, people thought there was nothing in there. It would all be optical in the outer parts. But we think this is a very bright X-ray source. OK. So this shows our 2D simulation. And it shows the luminosity per radius. And green is Shakura-Sanyaev. So you can see right away that you might expect it to be below this everywhere if the cavity were empty. But there's actually extra luminosity. So it's brighter far in, and also where the gas is hitting the cavity walls. So the binary disks are bright sources. Okay, and now the prediction had been before that if you look at the spectrum as a function of this is frequency and luminosity, in a normal disk you expect the spectrum to cut off at the temperature of the last gas that's in the disk. So for a single black hole, that would be the ISCO, the last stable orbit. But then if you had a binary, you might think if the innermost radius was this 2a, twice the binary separation, that would be at a much lower frequency. And you'd expect that the spectrum would cut off at a much lower frequency, right? We don't see that at all. So what we see is a very bright X-ray source. And what's going on here is that there's radiation from the mini disks, which take over at high frequency, and also all of this radiation from shocks in the accretion streams. So there's plenty of radiation coming through the disk. So some people have predicted there'd be a notch in the spectrum. We kind of see a little bit of a notch, but that's partially filled. Those are simulations that ignore the cavity, the radiation from accretion streams in the cavity. And so they don't see any radiation in this intermediate. They see this part, and then the mini disks, which they assume, but they don't see this part. We see that filled in by this stuff. So we predict before merger that these sources are actually bright instead of cutting off down here. There's all this extra radiation. And so that's really important. So that's going to be important for several things. And let me just make a technical point now, which is that the black holes have been accreting from this disk, and they're losing angular momentum. They're slowly spiraling in. But as we said, at some point, the timescale for gravitational radiation to drive them to merger becomes shorter than the timescale for them to evolve due to interaction with the disk. So they start to pull away. And so what we do here is, this is just a technical point, that in the outer part of the disk, we move the mesh with the Keplerian velocity. But then in the inner part, where the binary is, we have constant rotation of the mesh at omega binary. But then as the merge, and now we're allowing the black holes to merge due to gravitational wave emission. And what we do is we have the mesh kind of move at later and later times to get closer and closer. And that place where the mesh is co-rotating with the binary gets smaller and smaller until merger. So this, it's a little bit of a technical point, but it's really important because it allows us to very accurately track this accretion as the black holes move to merger. Okay. So this is the so-called decoupling phase. And what you're seeing here is 0.1 viscous times before merger. And so again, just to reiterate, there's plenty of gas around. The gas is quite close to the edge. There's streamers everywhere. And they're about to merge. Okay? Here they've merged, and they're totally embedded in gas. So they should be very bright during merger. And then 3 viscous times later, it relaxes to Shakura-Sanyaev around a single black hole. We didn't give it a kick. In reality, when the black holes merge, they can get a kick. And they also lose mass, which is another effect, which we didn't include in this calculation. So the key thing is the mini disks are persistent until right before merger. So there's plenty of gas there. And there's plenty of gas nearby that falls in right away. So here's what happens. So this is the accretion rate as a function of time. We start 3 viscous times before merger, and we allow the black holes to decouple. And what we find instead, people would predict that 1 viscous time before their merger, the accretion rate would go to 0. stay 0 until one viscous time after, where the gas would refill later. After the black holes merge, then there's a viscous time for the gas to fall in. So we don't see that at all. So what we see is plenty of accretion right up to merger, and it's still even at 10% during merger. So there's plenty of accretion going on. And then within a viscous time, as you'd expect, it relaxes back to the single black hole case. So, so there's high variability. So if you're looking for a source, you'd have high variability prior to merger. They'd merge, but with gas around, and then the variability would go away, the viscous time later. Okay, and so what do the spectra look like? Here, this is pre-merger, and you can see, again, that in the X-ray, and we scale it like this. So for these fiducial numbers, this is pretty high hard X-rays, but they're bright pre-merger. So this is two viscous times before merger, one viscous time before it gets even brighter as gas is flowing in. And then at merger, that goes away. Because all those accretion streams and all the mini disks are gone, and you're left with one black hole. And then a little bit later, you relax down to what we expected, which is the spectrum that's just truncated at the ISCO of that single black hole. So the signature you'd look for is the loss of high energy X-rays. Okay, and here, this is just another way of showing it. This is time over the viscous time. And so for the numbers that I showed in the last slide, at very high energies, it's bright at early times, and then it drops. Whereas lower frequency X-rays and also softer photons are steady. So you look for that diminution in the X-ray while the lower frequencies were constant. Okay, so the other question is, does the gas accretion affect the gravitational wave emission? And that's really an important question. And we can estimate that for what we've done so far, that the energy that's being kind of dissipated by the gas compared to the energy that's being released by gravitational waves is actually a fairly small fraction. So the simulations that I've shown to you, the gas is important for producing photons, but it doesn't compete with the gravitational wave emission, so it shouldn't modify it very much. But look, there's some high powers here, so it's very possible that in some cases, the gas can actually modify the gravitational waves, and that could be really important. This is an important area of research to look at now, which is, it depends, it's a very steep dependence on the binary separation. So future simulations, which we plan, are investigate the ability of the gas to alter the in-spiral rate and also of interest, possibly drive eccentricity. So the black holes are interacting with this eccentric disk, that those torques can excite eccentricity into the binary. And that could be very important for the signal that you expect in the gravitational waves. Okay, so the summary is that we've done simulations of circumbinary disk accretion using this moving mesh finite volume code. And the main point, if you're going to remember anything from this talk, is that the accretion rate onto the binary is not reduced at all. So gas efficiently enters cavities along streams. That's robust. The caveat that I should have mentioned is that in 3D, you can imagine as gas is flung into the cavity wall, it might puff up. So some of that mass may actually get into some sort of quasi-spherical cloud, and it might drive some sort of outflow. But I think qualitatively, a lot of that mass will be delivered back to the black hole binary, but that requires three-dimensional simulations in the future. Okay, and then for all of the mass ratios that we studied, we found that persistent mini-disks are formed, and that the accretion timescale of the mini-disks that we used exceeds the binary orbital timescales, so they're persistent. They're following the black holes around, and they're damping the accretion variability from the outer disk. And we also found that the mini-disk sizes are in rough agreement with analytic predictions by Timowitz and Lubo. We find significant periodicity in MDOT for mass ratios of interest, so 0.1 and higher. So there are the signatures we see are expected to be periodic. And also, binary torques excite eccentricity in the inner disk, and they can create this overdense lump, which can modulate the frequency, giving you lower frequency accretion rates, which if that translates into optical, let's say, variability of the light curve, would imply that the true binary frequency may be much higher, at least a factor of 5 higher than the observed frequency. And so for all cases that we studied, the accretion rate on the secondary is high enough that it causes Q to increase. So that might imply that we should expect supermassive black hole binaries to be close to 1. If they've had enough time to accrete significant mass, the secondary should gobble up most of it, and the mass ratio should be driven close to 1. So emission in the cavity can be enhanced relative to the single black hole case. This I find surprising. So these things are bright. They're not dimmer than single black holes. They're actually brighter. And the continuum spectrum in the X-rays is due to hot emission from the mini-disks and these accretion streams, and also the shocks driven into the cavity, inner cavity wall. And that's hot emission, so it should be quite visible in the X-ray, depending on the mass ratio and the mass of the binary. And then the other thing is that decoupling, so the time when the black holes decouple and are about to merge and emit the gravitational wave signature, it's not as abrupt as, so it doesn't decouple from the gas as abruptly as previously assumed. So these mergers should be wet. In other words, there should be plenty of gas around to make them visible in the electromagnetic spectrum during merger. The accretion persists until just before merger, and even during merger, it's not greatly suppressed. So these things should be detectable in both gravitational waves and electromagnetically, which may help a lot to understand them and also to discover them in the first place. Okay, thank you.
We have time for plenty of questions, I think.
Josh?
So, very nice, Andrew. As the mass ratio increases, what is the lump frequency doing? Is it becoming closer to the binary period or not? I thought I remember you saying it was, in which case you won't be necessarily underestimating period.
Yeah, okay, so for low mass ratio, you do see the binary frequency. So it's only when you get up to like 0.4. Let me show you that plot. Here it is. So you do see the binary frequency. And even at a quarter, you still see it, but it's kind of starting to be modulated, but it's still dominating. So it's only when you get up to nearly equal mass that it starts to take over. So, close to 1. So yeah, so absolutely important to emphasize, yes. For these guys, you are seeing the binary frequency. So you have to be close to equal mass before this is over.
And one other quick question. You said you haven't included radiation pressure.
Yeah.
I would think with this very hot, luminous gas that could be very important.
It's extremely important, and we actually have included it now, but I don't have any. I can show it to you. This is for a slightly different case, but we have. Okay, this is we have. This is actually a neutrino-dominated disk, and this one includes both radiation pressure but also degeneracy pressure. And this is an analytic solution, and we get actually. It's a different case, but it serves the purpose. We're actually showing the neutrino luminosity. This thing is as bright as the observable universe in neutrinos for a while. And it's amazing. I think, and as you can see, this that's only 100 kilometers. This room would be as bright as a galaxy. So this is a very hot disk that's accreting at a solar mass per second. So this is from GRB. This is from a GRB talk. But anyway, I just wanted to show you that we do know how to include radiation pressure, but we haven't implemented it into the binary simulations yet. But we'll do that very soon. I totally agree. It's extremely important.
Before you mentioned it, I was wondering how 3D would affect a lot of this.
Yeah.
And I realized 3D is much harder to do than 2D.
Yeah.
But I was wondering what your time scale was when we could expect some results of this nature in 3D.
That's a super important question. Yes, a lot of this. So the strategy is to kind of incrementally move away from things that we understand. So we go to 2D. We understand 1D disk, go to 2D. And then, but the code is 3D. And one thing that I want to emphasize is one of the design choices in making the mesh cylindrical is that we can domain decompose into annuli, which means it'll scale very well on large supercomputers, parallel supercomputers. And that's really important. That's very important for doing 3D. So it's in our plans. We are running 3D simulations now, but at too low of a resolution to show you. But when we run them more, and I would say in the coming year, we should have something. Or a year and a half. Let's be. I don't want to tie myself down.
Try and hold out.
Yes. Oh, yeah. You'll be. Yeah. No, don't worry. I'll come back and show you.
Well, you're considering a very interesting case with these double black holes, but of course, you know, the universe is filled with triples and higher order multiples. And
when are you going to do that?
Yes. In a year and 3 quarters.
And the radiation pressure.
Yeah. Actually, Paul Duffel, the student who wrote this code, is studying that in the case of planets. So he's looking at gaps, or basically cavities that appear to be in protoplanetary disks, and he's studying triples to see whether that can be the source of them. So we are kind of doing it. Not for this case yet, but yeah, someday.
So, Andrew, you have alpha viscosity, right? What do you do in the streams?
Yeah, so the heating due to the viscosity is completely unimportant in the streams because they're mostly radial. So we have it on, but it's not doing anything.
Okay, so it's there, but it's really
not doing anything because there's not a lot of shear in the streams. And those are being heated because of shocks. So it's material being flung onto them.
So all that luminosity that we talked about in the cavity is not from the
It's
viscosity.
not viscosity. That would be wrong because the alpha would not represent streams. It's only meant for the outer disk to drive mass into the binary. Yes.
Avoided that one.
Yes.
Do you expect that jets and this black hole spin will be important at all in this?
Oh yeah. So each of these disks that you see around each black hole is individually a quasar. So there could be jets. We didn't cover that obviously in this case, but we do fully expect there to be activity because there's accretion. So there.
I mean, but observational consequences, I mean, really make a significant difference over what you've got here?
Well, so the thing that I showed, the observation is in the optical, and nothing I predicted here would predict variability in the optical because the disk out there just thinks it's a Keplerian disk. It doesn't even know there's a binary. So in order for optical there has to be some magic that happens between the M dot and optical emission. And so that might involve some sort of jet-like phenomenon that I'm not claiming to model.
So if the black holes are 10 million solar masses, what are the actual timescales involved in this?
Yes, that's a good question. I do all of these scale-free. So, so I have to put in real numbers. I think I've got people that ask me, days, weeks, that kind of thing. Yeah. I don't know. We can
It's
do
all the
the
same
math.
to a theory.
It's about half and a half per 10 million per million. Yeah. Okay. Days. There you go.
So you have this eccentric disk.
Yes.
But does that affect the eccentricity of the black holes, and to what stage before the merger it still persists?
Yeah, okay, so that's exactly what I'm saying is an interesting thing to look into. If the separation is small enough and the disk is massive enough, yes, it can drive eccentricity. In fact, we're also interested in the case of planetary eccentricity, that eccentric cavities can drive eccentricity in planets. The same thing should happen here. So what I've showed you so far had low enough mass that it's probably not important because that L over L gravitational wave was really small. So it was really gravity that was in control. But for higher accretion rates, it can be important. So it may actually drive the binary to become eccentric. And we haven't,
circular mergers, are those calculations getting to be relevant?
Well, okay, that's a good question. So the strategy here is to be as kind of simple as possible. So we force the binary to be circular. And so we just calculate, and so then we force it to merge on the timescale for gravitational radiation of a circular binary. But you're absolutely right. There's asymmetric mass distributions around which can cause eccentricity to grow. So we have the capacity actually to allow the binary to become eccentric, but we haven't tried that yet, just because we want to understand the simplest case first. But you're absolutely right that it could be important. And I think it's it could be very important for predicting the gravitational waveforms.
Okay, last question. Yeah.
Wouldn't the presence of a magnetic field change the radiation spectrum and maybe even the dynamics?
It could if it were strong enough. So again, we use an alpha viscosity, hydrodynamics, circular binary, just to get a sense of what's going on. But in reality, we expect the disks to be magnetized, and that could affect the radiation, but we haven't calculated that.
Okay, so Andrew will be here through the end of tomorrow. Let's please thank him again.